So we've been adding up a whole bunch of terms in all these series, but it seems kind of tedious to add 2 plus 3 plus 4 plus 5 plus 6 and just to spend all that time adding numbers. There must be a better way. And before we talk about that better way, I gotta tell you a story about this guy right here. His name was Gauss, and he lived a long time ago. This is Gauss pictured as a young boy, probably 8 to 10 years old. In fact, people have said that I look a lot like Gauss, and I kind of have I think you can kind of see the resemblance here if I kind of put a hat kind of like this. And so I don't know. You decide. I think I look a lot like him. I don't think anything like him. He's a brilliant mathematician, and I'm just like a little small fry compared to this guy. But when he was a boy, there's a legend of Gauss. And he, for whatever reason, was causing a ruckus, as young boys sometimes do. And he was given a detention. And in this detention, his teacher said, Gauss, you must add up all the numbers from 1 to 100. And thinking this would take a long time. Think about it. It would take a while. If you're 8 years old and you're adding 1 plus 2. And now, they didn't have calculators and things like that. So he's adding 1 plus 2. Okay, that's 3 plus 3. That's 6 plus 4. That's 10. And that could be a daunting task. But the legend has it that Gauss thought about it for a few seconds, turned to his teacher and said, I know the answer. And he was correct, and she was amazed. And then he became this brilliant mathematician. But here's what he did. He kind of changed the problem. So you might think that we're just adding numbers 1 plus 2 plus 3 plus 4, blah, 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 blah. But he thought of kind of what happens on the other end. This is going to be, not only does it start 1, 2, 3, 4, but it ends 96 plus 97 plus 98 plus 99 plus 100. And what Gauss did is he kind of thought about the opposite ends of this series. And what he said is, well, if I take 1 and 10 and add those up, I'll get 101. If I take 2 and 99, I'll get 101 when I add those two things up. If I take 3 plus 98 and add those two up, I get 101. And this pattern continues over and over and over and over and over again, all the way until you get to the middle, until you get to 49 plus 51, and then really in between, that's 52, excuse me, and then you get 50 and 51. And so basically what we've done is we've taken the number 101 and we've added it up a total of 50 times. So what Gauss did is he multiplied 101 times 50, and he was able to find the sum like that without having to do all this long, tedious calculation. So that's kind of essentially what we're going to be doing with a little bit more formula help to help us out down the road here. So let's talk about this general arithmetic series formula. If I have some series, remember that an arithmetic series is generated by using the initial term and then its common difference. So if the first term is, I should really say, I'm missing kind of like a u sub 1 here. If the series formula is given by u sub 1 plus u sub 1 plus d, this is like our second term, u sub 2. U sub 1 plus 2d is u sub 3. U sub 1 plus 3d, 3 times the difference would be u sub 4, and so on and so forth until you get to this u sub n. Now, if any of this is looking a little confusing or mysterious to you, make sure you go back and watch some of those arithmetic intro to sequence videos. So what we can do then is we can take the sum of the sequence, or the sum of the series, I should say, for n number of terms. We can kind of write it out like this. The sum is going to be given as the first term plus the second term plus the third term, and we can take this all the way up to the last term, and then the second to last term, and the second to second to last term. And this is kind of encapsulating the entire series. Well, what we can also do then is we can kind of write this backwards. What if I wanted to write, rather than starting this series at u sub 1, let's start from the very final term. I can write it like this. So catch me what I'm saying here. See if you can believe what I'm saying, where I say that the sum is also equal to the last term plus the last term minus the difference, the common difference, plus the last term minus 2 times the common difference, all the way up to when I get the first term plus 2 times the common difference plus the first term plus 1 times the common difference plus the first term. So I've kind of just like flipped. I've taken this first line and I've kind of made a mirror image of this thing. Now what I'm going to do is I'm going to add up these two summations, these two series. And when I do that, over here I get S sub n plus S sub n, so it's going to be 2 times that sequence, or 2 times that series. And if you notice what's happening here, when I add u sub 1 plus u sub n, I get u sub n. When I add u sub 1 plus d and u sub n minus d, the d's will cancel, and I get u sub 1 plus u sub n. When I add u sub 1 plus 2d and u sub n minus 2d, again, the 2d and negative 2d, those reduce to 0, and I get u sub 1 plus n. And this pattern is going to continue over and over and over n number of times. So what we can do then is we can almost group all of these u sub 1 plus u sub n's together. Since there's n of them, I can simplify this and say that 2s sub n must equal n times these u sub 1 plus u sub n's. So what if I want to solve for just the series or the sum? I can divide both sides by 2, and I get n over 2 is equal to u sub 1 plus u sub n. So what we've done here is I basically am taking the first term and the last term, and I'm just multiplying it by n over 2, and that's going to give me the sequence, or the sum of the series. Now we also know u sub n is given as u sub 1 plus n minus 1 times d. So what we can do is really at the end of the day, if you weren't able to track with some of this, I'd say pause it and just kind of let it sink in or look it over again. But really the big takeaway at the end of the day is these two formulas we can gather from this process. These are the two formulas to generate the sum of a finite series that is arithmetic. So really what we need to piece together here is we're familiar with n, we're familiar with u sub 1, we're familiar with u sub n, we're familiar with d. Really the only different term thing is this now s sub n. That's, again, that sum for an n number of terms. The really important thing is that this is only for arithmetic series. Only. This does not apply to geometric, only when we're talking arithmetic. So let's put this thing into practice. Let's use this example where we are finding the sum of 4 plus 7 plus 10 plus 13 all the way up to 50 terms. So first of all, we know that this is an arithmetic sequence. We know that the first term, u sub 1, is equal to 4. That's this one. We know that the common difference is equal to 3, since I'm adding 3 in my sequence. And if I want to find this up to 50 terms, that also gives me my n value, 50 terms. So between those two formulas, we kind of have to make a decision which is the appropriate formula to use. And I'm going to use the formula that looks like this. S sub n is going to equal n over 2 times 2 u sub 1 plus n minus 1 times d. And the reason I chose that formula is because you'll notice that I don't know what u sub n is, but I do know what u sub 1 is, I do know what d is, and I do know what n is. So this is the formula to choose for me. So the sum of 50 term series is going to be given as 50 over 2 times 2 times 4 plus 50 minus 1 times d, which is 3. All right, now this is just simplifying. The sum of 50 term series is going to be given as 25 times, this looks like 8 plus 49 times 3. And if I take this out a little bit further, I'm going to get s sub 50 is going to be 25 times 8 plus 147. And the sum of a 50-term series with this arithmetic sequence is given as 3,875. So look at all the time you saved rather than adding up these numbers 50 times on your calculator, or even worse, by hand. So why don't you try this example? Oh, no, we got one more example. That's right. Let's do this example first, and then I'll have you try a couple like it. This one's very similar to the last one, but slightly different. Again, we're going to look at what we know. We know what u sub 1 is. We know this is that's equal to negative 6. We know this is an arithmetic sequence. We are adding 7. So this is going to be a common difference of 7. But this time we don't know what n is. So it might seem like we're kind of out of luck. However, we do know what u sub n is. U sub n is 141. So now when I'm deciding which of the two formulas to use, I'm going to use the one that uses this information, u sub 1, d, and u sub n. So the sum of n terms is going to be given as n over 2 times u sub 1 plus u sub n. This is the formula that I'm choosing to use here. All right, so then s sub n is, or rather s sub n is going to equal, well, actually, I take it back. We do need to figure out what this n is, since I'm needing to use n in this formula. So actually, let's figure out what s sub n, or rather what n is. So in order to do that, I need to find some way to relate this term in the arithmetic sequence. So remember, I can use the formula u sub n equals u sub 1 plus n minus 1 times d. This is like the definition of our general term in this arithmetic sequence. So now I do know what this is, I do know what this is, I do know what this is, and I'm looking for n. So 141 is going to equal negative 6 plus n minus 1 times 7. All right, and let's do a little bit of algebra here. Let's add 7 to both sides. This is 147 equals 7 times n minus 1. We'll divide both sides by 7, and this looks like 21 equals n minus 1. Therefore, n must equal 22. So now I actually do know what this is. And I guess since I know all 4 of these terms, I could use either one of those formulas, but I still like this one better. It's kind of fewer steps in my opinion. So now I'm looking for s sub 22, and that's going to be equal to 22 over 2 times negative 6 plus 141. So s sub 22 is going to equal 11 times 135. So s sub 22 at the end of the day is going to equal 1,485. Okay, so a little bit more labor intensive since I don't know what n is. And again, you do have to kind of go back to your original general term formula, and then you can use that n in your summation equation. So now I've got 2 examples that I'd like you to try. Try one similar to that example 3. So pause the video, give this one a shot, and we'll see how it goes. All right, and so here is my workings out for this one. We do know what n is, we do know what u sub 1 is, and we do know that the common difference is 4. So once we have that information, we could just use that second formula and go from there to get the sum of 20-term series is 820. All right, in this final you try video or problem for this video, we have this sequence where we want you to add up 5 plus 8 plus 11 plus 14, and this pattern continues all the way to 101. So please find the sum of this series. Pause the video, see what you know, see what you have to figure out, and give this one a shot. Okay, and here is the solution that I have for this one. I kind of figured out that n is equal to 33 by doing a little bit of algebra over here, and then I plugged in all the information to get the sum of a 33-term series is 1,749.